Dear students, in the previous lecture we have discussed the basics of laser construction and what is the importance of laser when you compare with your LED. Today the lecture is about the resonant frequency of laser. So we know that one of the main element in the laser is a resonator. It is a amplification medium. So it is also it consists of, generally you can see here, it consists of two mirror. It consists of two mirror. Generally to produce the, it will provide the optical feedback. It's provide the strong optical feedback in the medium, right? Especially in the longitudinal direction with respect to the length of the cavity. That is in the longitudinal direction. To examine the resonant frequency of laser, we need to follow the steady state condition. What is the steady state condition? Why you need to follow? We used to say that is called steady state oscillation. Why we need to go for that steady state condition? The reason is, to if you reach that state, that the laser output will remain consistent without any significant changes. So that's why we need to maintain the steady state oscillation in the laser. To achieve that condition, one of the important condition is e power minus j2 beta l equal to 1. That is, beta is the propagation constant, l is the length of the cavity, and we know that the round trip, the entire round trip, one round trip of the cavity is 2l, between 2 and fro, one round trip. Already we studied in the class. So the strong relation is, to have a steady state oscillation, e power minus j2 beta l should be equal to 1. We know the basic relation, that is e power j theta equal to 1. So theta should be the multiple of 2 pi. M is an integer. So if you look at this condition, in place of theta I can bring 2 beta l. So I can rewrite as 2 beta l should be equal to 2 pi m. M is an integer. So if you cancel this 2, what is the m? M is a beta l by lambda. So we know the condition, beta is a propagation constant, that is 2 pi n by lambda. If you substitute here, what you will get? M equal to 2 pi n by lambda into L by lambda. So if you can cancel the pi, and we can rewritten as M equal to 2nL by lambda. Also this M also can be written as M divided by L lambda by 2n. So I can, both are same, right? Here what I have done, this 2n I am taking to the numerator, so it becomes M equal to 2nL by lambda. So from this equation what we can try to say is, M should be, that is the cavity resonant, that is a integer, is the integer number of M of half wavelengths, the span region between the mirrors. So that means if the wavelength of light is 500 nanometer, the distance between the two mirrors should be the 250 nanometer. Then only the lasing cavity will resonate. Then only it will line up with perfectly. That is, it line up perfectly. That means it will ensure that the light waves will reflect back and forth, and the cavity reinforce each other constructively, leading to the strong laser emission. It should maintain this condition. That means the cavity resonate when the integer number of L is the cavity length of the cavity, lambda by 2n is your half wavelength. That is a half wavelength, the span region between your mirror. So that's what I said. If your wavelength of light is 500 nanometer and the distance between the mirror should be 250 nanometer, then only the lasing action will be perfect. then only it will line up perfectly. That's a condition we need to maintain. So with that understanding, you understand that m equal to 2nl by lambda. We know the strong relation, that is c equal to v lambda. That is inverse of wavelength is nothing but a v by c. That is a frequency by the free space of light. If you substitute here, if you bring this condition here, I can rewrite as m equal to 2nvl by c. That is a m is nothing but a 2nvl by c. So now we know that, consider you have two successive frequencies of frequency that I need. See, let me say this is your mode m, this is one resonant frequency, this is a adjacent frequency, let me say this is m minus 1. I want to find what is the difference between these frequencies. I can say like a del v or del lambda in terms of frequency, in terms of wavelength. We know the strong relation del v by v equal to del lambda by del. So this condition we are going to use, okay, in the coming derivation. See, that is m is nothing but your mode at the resonant frequency. That is a v is a frequency. That is a resonant frequency at m mode. 2n vm l divided by c. That is for m mode. When you say for adjacent mode, that is m minus 1 equal to 2n vm minus 1 L by C. Now I want to find what is the difference, then only I can find what is the del V or del lambda in terms of wavelength or frequency. That means I want to take a difference. That means m minus 1 equal to, so what is the m? M is nothing but 2n Vm L by C minus 2n Vm minus 1 L by C. So you can cancel these terms, right? So you will get 1 equal to 2 Ln by C. I'm taking the common term outside, so you will be getting Vm minus 1. So with this, the difference of this, that is a Vm minus 1 is nothing but a del V, what we said, right? This is a Vm. This is Vm minus 1. What is the difference? That is a del V. So I can bring this relation, right? So if you bring this relation, I can write del 1 equal to 2 Ln by C into del V. That's what here it is written. So that is the difference between this V frequency minus Vm minus frequency, that is nothing but del V. So this is your m, this is adjacent mode m minus 1. So please understand, your laser will emit few modes. There is n number of modes, but let me say this is your laser, it will emit a few modes. But when you go for LED, it will emit more number of modes. That's why it is a non-coherent. But when you take a laser, it will emit a few modes. Okay, that is why laser is coherent source, right? So from this understanding, we rewrite from this equation del V equal to, if you rearrange, that is C by 2nl. That is your frequency spacing is nothing but C divided by 2nl. With this understanding, we are going to the next relation, that is, as I said earlier, that is a del V by V equal to del lambda by L. That is a relative change in the wavelength of light divided by the original wavelength equal to, directly proportional to the change in the frequency divided by original frequency. With this condition, I can write this what we derived in the previous condition, that is a del V equal to C by 2nl. We know that C equal to V lambda, so I am substituting instead of C, V lambda. So I am bringing this V to this down, so that this will become like this, that is del V by V equal to lambda by 2nl. This is what we derived, right? Now I am bringing the strong relation, that is del V by V equal to del lambda by lambda. So I can rewrite like that, right? So that means I can write like del V by V equal to del lambda by lambda. So I want to find what is the wavelength spacing between this and lambda. This were lambda m minus 1, right? So this is a adjacent mode. If you calculate the del lambda is, you bring this side, so we'll get lambda square by 2n. This is what final equation what we derive. So conclusion is, this is your laser your emission. This is a Gaussian output profile. We consider Gaussian output profile. This is a longitudinal modes, right? This is a longitudinal modes. Whatever mode which is greater than, that is a G equal to L. The gain is equal to L. Those modes will be exist in the spectrum. So here you can see, here this is what we calculated. So the adjacent spacing between the frequency is del lambda. Del lambda is nothing but your lambda square by 2nl.